We now move on to a fireside chat titled Securing a Connected but Fragile World. The speaker of the session is Steve Grobman, Senior Vice President and CTO, McAfee LLC. Steve leads McAfee's development of next-generation cyber defense and data science technologies and threat and vulnerability research. Prior to joining McAfee, he dedicated more than 2 decades to senior technical leadership positions related to cybersecurity at Intel Corporation, where he was an Intel Fellow. The session chair is Akhilesh Tuteja, Partner and Head Digital Consulting, KPMG India. Akhilesh serves as the Global Cybersecurity Practice Co-Leader and heads the IT Advisory Practice for KPMG in India. He also leads and heads the Risk Consulting Practice for KPMG in India. Over to you, Akhilesh. Take it away.
Good morning, everyone. Thank you very much, Shreya, for that nice introduction. I can't tell you how happy I am today to be with you, along with my friend Steve. Before we get into the conversation with Steve, which I'm sure will be exhilarating, I want to tell you 3 reasons that you must stay stuck to your seats for the next 20 minutes. The first one, this is going to be possibly the coolest session NTLF has ever hosted, and I'll tell you why. And the second one, all of you who made great careers and made enough money in technology using classical computing, I can tell you, you can multiply your money several folds because quantum computers run at several fold speed. And last but not the least, I will tell you why is it important for you to stay in this session so that you don't lose your hard-earned money because one of your supposedly good friend could defraud you. So with that, let me jump into the conversation with Steve today. Thank you, Steve, for joining us. What I would like to do, and I know being in NASSCOM for many years, that people here have a very different understanding of technology trends. Some of us may like to understand more, and there are others who are expert. But let me start with my first question to you, Steve. How do you explain quantum computing to a 5th grader?
So first off, thanks so much for having me. I really look forward to discussing this topic. It's a topic that can seem intimidating because even the name, quantum computing sounds like you need to have a deep understanding of quantum physics in order to understand some of the issues, challenges, and benefits. But what I'd like to do with you is simplify it. So I love your first question in talking about how can we take such a potentially complex topic and make it something that everybody can understand. One of the things that we've been working to do in computing for a long time is make computing go faster. I started my career at Intel, where one of our founders was Gordon Moore, and Gordon Moore was famous for having Moore's Law, which essentially said that computing speed will double every 18 months. And sure enough, Gordon Moore had this fabulous intuition that turned out to be right. But the other part of computing is around parallelism, which means how do you do more than one thing at a time? So when we think about quantum computing, it's not really so much about having computers go faster, but it's taking this concept of being able to do many operations in parallel at a very different order of magnitude than we've ever seen. So if you think about quantum physics, where it has this concept where things aren't necessarily in one state or another, but they can be in 2 states at the same time, it's that principle that allows you to do things in massively parallel. And, one of the topics I know we're going to discuss is how quantum applies to crypto encryption. And I think one of the ways to explain the benefit of a quantum algorithm and why this parallelism is important is to take your 5th grader question and apply it to encryption. So I'm going to actually ask you a question. And because I don't have any slides, we're going to try to make this a little bit visual. If I brought you a square, so a rectangle, and I had marbles that had 5 marbles going in one direction, 7 marbles going in the other, and it was all filled out, how many marbles would I have in that rectangle? So 5 by 7 is...
Unless it's a trick question, I would risk by saying 35.
Okay, that's right. And for everybody watching this, there was no collusion, so we did not talk about this problem. So I will assert that you are able to do 5th grade math and multiply 5 by 7. Now, if you take that same problem, would you agree that any rectangle that I brought to you, that as long as you could count the number of marbles on each of the axes, it would be pretty simple to multiply? So if I up my numbers a little bit and I said I had 23 on one side and 17 on the other, I'm not going to make you do the math. Multiplying 23 by 17 is actually pretty easy. That's a problem that really any 5th grader could do. It would be 391.
Yeah.
Now I'm going to make it harder. If instead of giving you a beautiful rectangle, I just gave you a bag of marbles, and you can count the marbles. So I hand you this bag of marbles, and I'm going to even tell you, so I'm not going to make you like go 1, 2, 3, 4, 5. Like I'm going to tell you there's 551 marbles in my bag. And now your challenge is to find the one and only one perfect rectangle to place those marbles in. Well, it turns out that this is a very difficult problem. And what I just described is the underlying math that makes all of the encryption that we use today possible. There's this phenomenon that says if you take 2 prime numbers and multiply them, you get their product. And it turns out that that product will only fit into a single rectangle of the 2 prime dimensions. So it's a what we call a one-way problem, where it's very easy to do one way and very hard to do the other. So I asked you the 551 bag of marbles, like what you would need to do is you would need to say, well, I'm going to try 3. And you would say 3 divided by 551. Okay, that's not an even number, so there's going to be spaces left. So let me try 5. And then it's going to turn out that you'll have things left. If you did all of this, I'll give you the answer. It's 19.
Because I studied in Indian mathematical system, I can tell you the answer is 29 by 19.
That's right. That's right. So I'm very impressed. And you if you did that for bigger numbers, you're essentially needing to iterate over a very large number of testing various solutions. And so if you think about the way that a computer would attack this problem, it would break it up. So you can think of, you'll give one computer test all the numbers between 1 and 5, and then another computer between 5 and 10, and they could all work in parallel. What quantum computing does is it makes it so that you can run some of these parallel types of tasks essentially instantaneously to get to that. And I'm like shocked, honestly, that you're able to do the factorization. And did you do that in your head?
As I said, that I studied in Indian mathematical system. We know our numbers.
Okay. I thought I was going to stump you. I am incredibly. Maybe we don't need quantum computing. Maybe we just need you. So.
No, it was rather easy because 551. You get closer to 2 numbers. You're closer to 10. So 29, 19. It's just a good sheer luck.
Sheer luck. But anyway, so it's understanding that there's this class of problems that massive parallelism is incredibly helpful for, that a different type of computing will change the dynamics. And that's really the way we need to think about it. And there's a lot of problems that will be good for humanity that we can throw at this, whether it's working on developing drugs to help with the next pandemic, or identifying new materials that will help us with global warming. Quantum computing has a lot of power to solve some of the mathematical challenges that we just don't have the ability to do with today's computing.
Absolutely, Steve. I think as I heard you explain in the simplistic term, I got the understanding even better. So the way you explain the concept of one-way computational and factorization is one of the big problems. But I do want to share with all our audiences here that quantum computing is very fascinating. To start with, it is the coolest thing to have. And why I say it's the coolest thing? Because the quantum computers actually run at a very, very low temperature. If you didn't know, the room temperature which I'm in right now is somewhere around 300 Kelvin, and a quantum computer would be running more like a 3 millikelvin. So they're really, really cool things to have. But at the same time, I also want to talk about, as Steve mentioned, that there is a part of the problem which quantum are able to solve much easier, like reversing the factorization, and therefore it presents a significant challenge to some of our encryption which we have today. I do want to talk about that. People didn't sit in the rooms and say, hey, we want to build a quantum computer because we want to break the encryption. Yes, that would be a great thing to do as well, but it's not the same purpose for which it's built. So quantum computing has a great history and, of course, a brilliant future where we are going to use quantum computing to actually solve a lot of hard real-world problems. One of the big problems which Steve mentioned about, studying the material, and one of the things which the classical computers have not been able to solve is because material, as we know, at a subatomic level, are very uncertain. Like most consultants, they are generally uncertain. They give the answer depending upon what the state they are in. So the atoms and the subatomic particles are in a state of uncertainty. Heisenberg told us that. And it is very hard to simulate that reality. And what the quantum computing does is that it uses the same property. So it's like hits them with the same property they have and solve a lot of problems. So simulating the world, simulating, identifying new material, identifying new ways to solve the problem is one of the great benefits of quantum computing, which we'll see. But I want to go back to Steve, and Steve, to you. You explained to us that the cryptography is something which certainly is at risk because of some of these quantum areas. But we also know that the cybersecurity is also a field which is benefiting from quantum for things like the quantum key distribution and some of those areas. So tell us a little bit more about your perspective on how even the cybersecurity experts can take advantage of the growth in quantum computing.
Sure. So, when we think about securing data, it's all about having the people and the systems that you want to have access to the data to always have access, and nobody else. So all of the people and adversaries that you never want to have access to the data, they never are able to get access. And what we've done with encryption is we've built a number of interesting paradigms that has been able to set this up. So in cryptography, we generally have two types of encryption. We have what we call shared key encryption and public key encryption. Shared key encryption is something that is very easy for people to understand. It's where you take some data and anybody who has the key, you can think of a key like a password, would be able to decrypt the data. So if I took a chunk of data and encrypted it, and then I told you, I said, hey, the key is dogs and cats living together, like then you would know that like anybody who had the phrase dogs and cats living together could decrypt that data. One of the things that quantum key distribution does is it makes it so that you and I can both end up with a very strong key in a way that we know that nobody else has been able to find it. The other type of cryptography that is potentially going to be impacted by quantum is what we call public key cryptography. And this is a little bit more difficult to understand, but it's very interesting. When you encrypt data with one key, the key that you encrypt the data with actually doesn't decrypt the data. There's a key pair, and one of the keys encrypts and the other key decrypts. And you might say, like, why would I want two keys? And the reason is, with public key cryptography, it allows anybody to encrypt data so that they can send it securely to somebody else. So for example, if you have a private key and then you tell the world your public key, and you can do that. That's why it's called a public key. It's literally out there for everyone. Anybody can take that public key, encrypt the data. Once it's encrypted, the public key isn't useful to decrypt it, but they can then send it to you, and you're the only one in the world that can decrypt it. And it's this type of cryptography that is potentially going to be broken as quantum computers become more practical. And that's one of the things that, I've talked a lot about and am thinking a lot about, that we really need to recognize that there are a lot of organizations, governments around the world that would want to read all of the data that's been encrypted over the last 30 years. We need to recognize that part of the problem with encryption is it's not just about safeguarding what we're encrypting today, but it's, what I sent you yesterday and 3 years ago, and what I'm sending you today that I want to stay secret in the future. So it's all of those things that we need to really think through.
That's interesting. And I think for those of us who've not been through the public key cryptography, it is very hard to understand that how can I use a key to lock the door and use a very different key to unlock the door. But as you explained, that these are some of these things, by using quantum computing, we could actually make life easier in many ways, but also need to be careful, because the same thing, it's the same weapon which can be benefiting and also destroy. I'm conscious of time, but I'm really enjoying, Steve, this conversation with you. So let me ask you one thing about, how some of those things, as I hear in the world of cryptography, also Bitcoin. So I've been told that, the best way to get rich in today's time is to mine Bitcoins. And mining Bitcoins also requires me to do a proof of work, which means that I need to create some sort of a cryptographic outcome for the hash, which matches, of course, without getting into too much detail. But for those who haven't played with Bitcoin particularly, if you wanted to become rich without having to invest a whole lot of money, you could buy a small machine to do the Bitcoin mining. And all your machine needed to do is to find the next number, the magic number, which is typical of the nuance, which is again identified by, as Steve mentioned, doing the factorization, applying the algorithm on a hash. So Steve, question to you, that if I had access to quantum computer, could I mine Bitcoin faster and turn rich overnight?
Not really. And the reason for that is quantum computing, while it's useful in certain problems, it's actually not useful in others. And this is actually a misnomer that a lot of people have, is they think that, when quantum computing becomes practical, quantum computers are going to do everything that traditional computers do better. And that's not at all the case. It's going to be very workload specific. So today, standard computing technology is expected to perform certain types of problems much more effectively than quantum computers. Like if people think that their laptop in 20 years is going to be quantum computer powered, it probably won't be, for a whole host of reasons. Number one, as you mentioned, most of the technology today is operating at obscenely cold temperatures. maybe we should have strapped a quantum computer to the James Webb Telescope. It would probably work pretty well on the cold side in deep space. But for most practical applications, standard computing is going to still be the more practical approach. Even in cryptography, there are certain types of algorithms that quantum computing aren't really going to help break. So, you mentioned hashing as it relates to cryptocurrency. When we look at hashing or the ability to break hashes or symmetric encryption, as we discussed a little bit, like these are both thought to be quantum safe, meaning that we don't believe the types of algorithms that quantum computing will be able to use to solve other types of problems, like the factoring problem that we started with. Those don't really apply to symmetric encryption or hashing, which is widely used in cryptocurrency. Now, people securing their cryptocurrency wallets using traditional public key encryption, those are some areas that we need to be aware of and ensure that as quantum computing becomes more practical, that there aren't issues there. But I don't think the entire ecosystem around cryptocurrency is going to come crashing down as quantum computing makes more progress. With all of that said, I do think cryptocurrency is a great lesson in asking the question, how do we want to use our compute resources? You said that if we want to mine cryptocurrency, we just need to run some algorithms on a computer. But for most people today, the economics are that electricity is going to be more expensive than the cryptocurrency you'll actually be able to mine. As you point out, while quantum computers can be used for a whole host of capabilities, I think we as a society need to decide how much of that power do we want to apply to solving global warming and health and medicine, as opposed to identifying how to, use it for purposes like breaking encryption and things that, clearly have value to intelligence organizations around the world. But we want to make sure that there is focus on the benevolent benefits that quantum will bring as well.
Thank you. Thank you very much, Steve. This was very, very enlightening. You told us very clearly that even if you had access to quantum computer, you can't become rich overnight by mining more Bitcoins. But if your supposed friend, who is actually not your friend, has access to quantum computer and you were using the public key to protect your wallet, watch out. She or he might be able to defraud you and take away all your Bitcoins. I wish if I had a quantum computer, I could have done some sort of entanglement with the clock and carried on a little bit longer, but we all live within the world of the natural clocks, and I'm getting this signal that time is up. I certainly enjoyed, Steve. I hope you also enjoyed this conversation. I'm sure everybody who's watching this would have enjoyed as well. So with that, thank you very much, Steve, for sharing your time with us. And I get back to you, Shreya. Thank you.
All right. Thanks so much for having me.
Thank you, Akhilesh and Steve, for an insightful session and telling us what quantum computing is going to be about. Quantum computing solves problems like reverse factorization, quickly posing a challenge to encryption. Quantum computing has a great history and a brilliant future where we're going to use quantum computing to solve a lot of hard real-world problems. And with public key cryptography, it'll allow anybody to encrypt data to send it securely to anyone else. This type of cryptography that's potentially going to be impacted by quantum computing is public key cryptography. Quite a few interesting concepts there.